Let's take a long spring. Now fix one end against a rigid surface and the other end we hold it in our hand. Now let's alternatively push and pull the spring. What do you observe? You will see that some regions of the coils of the spring come close to each other and some regions they move apart. And these regions which come close to each other, they are compressions, and the others, they are rarefactions. You see something? The compressions and rarefactions are the alternative regions, one after the other. And these regions form a wave that is traveling along the spring. Now, what is the direction of this wave? Okay, I'm going to make a complicated statement. Listen to me very carefully. The direction of the wave in the spring is parallel to the direction of vibration of regions of compression and rarefaction. Shall I repeat it? The direction of the wave, well, that is parallel to what? The direction of vibration of regions of compression and rarefaction. So, what did we see in a stretched spring? We saw the propagation of the longitudinal wave. Do a nice little experiment. For that, we need a table. So let's place a table close to a wall. Now we take two hollow plastic tubes. They should have a sufficient length and diameter. Fine. Now arrange them on the table like this. Now all you need to do is place a table clock near one end of one of the tubes. Now try to hear the tick-tick of the clock through the other pipe. But make sure that the pipes are on the table at some distance from the wall. Fine? You will have to do some adjustment of the other pipe so that you can hear a loud tick-tick. Now our experiment is almost over. Mark the positions of the tubes on the table. And now measure the angles of incidence and reflection. Obviously, you can use a protractor for that. And you will find something interesting, but not unexpected. They will follow the first law of reflection. So both the angles will be equal. Now you lift the second tube from the table to a height and try to listen again. Can you hear anything? I'll not give you the answer. Do it yourself.
Application of multiple reflection of sound. Now, multiple reflections are made use in our daily life in variety of forms. Few of the basic applications are in case when we have to make a sound heard in a large auditorium. In that, what is made is that the surface and the walls or the roof of the auditorium is made in such a way that most of the sound get reflected at different angles, so that the sound produced by the speaker can easily be heard all over the auditorium through multiple reflections. Other application of multiple reflection, or we should say of echo, is in case of sonar. A sound wave is used to detect the irregularities or the special features of the seabed. It is not easier for human beings to always dive till seabed and see what is visible or what is available at this level and how the seabed is made. Instead of that, what we make use is we send a sound wave which interacts with the seabed and get reflected back to the ship again. The amount of sound wave reflected and the kind of sound wave reflected back to the ship determines the nature of the seabed and if any irregularity or a special feature is available can be detected easily. Another application of reflection of sound in modern day physics is detecting any irregularity present in a given material without actually breaking that material. What we do is we make use of a sound which is of the same vibration or the same wavelength, that is of the size of the atoms in that material. If both have the same kind of vibrations, they will move in a straight line and they will going to just pass through the material directly. But if there is happens to be an irregularity, that irregularity will behave in a different way and our sound will going to hit that irregularity and rebound back in the same direction. This detection can easily tell us the nature, size and other properties of that irregularity. This is the same phenomena what we make use in an ultrasound in case of a pregnant woman.
Every sound is produced with a specific disturbance. Larger the amplitude, larger is the loudness and vice versa. Larger the frequency, larger is the pitch and vice versa. Effect of sonic boom. Fruit falls down from the tree.
You see these two guys on the screen? Now one of them whistles and the other one listens. How does the sound travel? It's actually traveling through air. Sound needs a medium to travel. It cannot travel through vacuum. You don't believe me? Let's do a small exercise. Take an electric bell. Now let's hang this bell in an empty glass jar that's fitted with an air pump. You see that? Now initially you can hear the sound of the ringing bell. Now let's start pumping out air from the glass jar. That's what we have the air pump for. What do we find? The sound of the bell decreases. And if we continue to pump out air, then there'll be a point when the glass jar will have no air. And this is precisely the point when you will not hear any sound from the bell. So why did that happen? It happened because when there is no air inside the jar, well, there is no medium for sound to travel. And sound, as I told you, cannot travel through vacuum.
The tuning fork is hit with a rubber pad to set vibration in it. In this manner, it produces sound. The vibrating tuning fork is touched with the hanging bulb. The simple pendulum oscillates. It shows that sound is a form of energy. The tuning fork is hit with a rubber pad to set vibration in it. In this manner, it produces sound and is touched with the hanging bulb. The simple pendulum oscillates and it shows the sound is a form of energy.
You see this big building or this bridge? You know, there is a lot of metal which is used for making these. And if there is a flaw or a crack, you can imagine what will happen to the strength of these structures. Thankfully, we can use ultrasonic waves to identify those flaws. To understand it better, let's look at this setup. You see, there is a computer, there is a pulsar receiver, there is a transmitter and a receiver. Now what actually is done is, you move the transmitter and the receiver together over the surface of the metal. Can you see that? While you do that, you get a graph. And when there is a crack, the ultrasonic waves are actually reflected. And that shows in the graph in the form of a peak. And that's how you detect a fault or a flaw in the metal.